Okay, it's there. So in the last class, we have given an overview of the Prolog language and we were working on some examples. So let us continue that. So we were focusing on the list data structure and we were kind of writing different programs related to lists. So one particular program that we might want to write to delete an element from a given list, right? So you are given with a list, an element to be deleted, and if the element is there, you should delete it. So the way that we'll be thinking is that we first need to check out the base step. So what would be the base step here? So basically what you have, it is very simple to follow. So this is the kind of element that you want to delete. So if X appears in the first position of the list, so our output would be L1, right? Now, what is the recursive step? So with this example, I want you to get acquainted with the recursive way of writing the programs, right? So again, we have got X to be deleted. And if we have a list like this, if we have a list like this, and we obtain as, we have something else than X, let's say Y. So you'll be coming up with an output list, which is say YL2, because Y is not matching with X. So Y should be there in the list, output list, but we have to find an X from L2 and delete that. So our recursive call would be, so delete X from L1 to give us L2, right? So let us look at the program. So this is the snippet that I am highlighting that concerns this deletion of an element from a list. So this is the base state where we have this element to be deleted. And this is the list where the first element of the list is the X, which we want to delete. And the output of this deletion result will be L1, right? And in the recursive step, we have X to be deleted. This is the input list YL1. The output list is YL2. That means we need to delete X from L1 to get L2, right? Now, the next program that we will be focusing on is whether a given list is ordered or not, right? So basically, again, we'll be going to the base state. So what would be the base steps? So the first one would be if we have an empty list that will be ordered, of course, right? Also, if we have only one element in the list, that will also be ordered, right? Now let us figure out the recursive step. So one thing that I will like to tell you that this is one way of representing the thing, but there might be other possible ways by which you can achieve the same goal, right? So what we have got one list which has got one first element to be age and the remaining part of the list to be tail, right? Now let us conceptualize another list. So here I'll not say another list. I'll try to represent the same list differently. So what is the difference? The first element of this is 8. I'm dividing tail into two parts. One element H1 and then followed by tail 1. So what I am doing, I am dividing I'm dividing this tail into two parts. The first one element is H1 and tail n. So basically, we are doing tail equal to concatenation of H1 and tail 1. Something like that. So you don't take this in a programmatic view. So I'm just telling you the strategy, right? So the first thing that we need to check in order to see whether they are in order or not. So you need to first check whether H1 is less than equal to, sorry, H is less than equal to H1 or not, right? So this is what we'll be checking first. Then we will look this H1 tail 1 to, or tail is a result of concatenation of H1 tail, right? If that is so, then what would be our sub goal? Our sub goal will be whether this list is ordered or not. So I'm processing the things pair element wise. So we are taking two elements, trying to compare, and then we are moving to the recursive step, right? So that's the way we are following. So let us have a look at the program. So we have the base step, like the empty list is an ordered list. And if you have one element in the list, so that is also ordered. And if you have one element, like the first element to be H and the remaining to be tail, first we'll concatenate this H with tail 1 to get tail. So this is another way to say that we are dividing tail into two parts. One is H, one singleton list, and another the remaining part of the tail, right? Then we are checking, after extracting H1, we are checking whether H is less than equal to H1 or not. And then we are checking whether H1, tail 1, if we combine them, we have a list. Basically, we are pushing this tail for checking this orderedness or not, right? So that's how we can go forward. But again, so this is one way of saying this. So that there is another implementation where you do not need to use this concatenation function. So you might want to use, say, membership function or something like that, right? Now, the third program that we will like to write is to compute a maximum in a list, right? So again, the base step is so you have X, then X is the max, right? So what is the recursive step? So again, basically we'll be dividing the list into two parts. The first element and followed by a tail, right? Now, we will call this program recursively to find the max of tail, and let us assume that N1 is the max of tail. Now, the next thing that we'll be doing, we'll be checking two things. If H is greater than N1, then our the output, which is N, is H. So max is H. Let me write max or M. Or if H is less than equal to N1, then M is N1, right? So again, let me go to the recursive step because the base step is pretty straightforward. So I have divided the list into H and tail, and N will store the max value. So I'm first computing the max of the tail, which is N1. I'm checking whether age is greater than N1 or not. If that is so, then we assign age to N or else. So this is the else part. So if this is not satisfied, then the program will go into this, go to this room, right? So with this, let me go to a consolidated way of representing a world. So our world is a robot that is manipulating the blocks on that is kept on the table, right? So you'll be working on these kind of toy problems very frequently. I guess you have already started working on this. So the first thing that we need to understand the description of the world. So basically there are 5 blocks in this particular world, and the table is divided into or represented as a grid, and the robot, it can see from the top, from the ceiling, right? That means only 3 blocks in this world are visible to robots. So how do we represent this information that A, D, and C, these are the 3 blocks that are visible. So whenever a robot can see a block, can also know the coordinate of the block or the position of the block. So that means the this predicate like CA15 is true for the robot, right? CD45 is also true for a robot, right? Now also we have the positional relation of the blocks. So how do we do that? So basically I'm saying that A is on block B, B block is on C, C block is on table, D block is on table, and E block is on table, right? So this is my description of the world. Now, these are the questions that I like to ask given this very small toy problem. So the first thing that I like to ask is, what are the blocks in this world? So I will like to ask this question from you. So if anyone can volunteer from you, that will be good. So how write a query that will try to address this question like, what are blocks in this world? So basically, I'll try to list all the blocks in this world. How to go about it? Any idea? Himadri?
Yes, sir.
So I'm asking, so if we have a world description like I have mentioned, now I want to ask a question like, what are blocks in this world? So how we can write a goal for this? Basically, finally, you have to write a goal, right? So what would be
Yes.
the,
The goal.
yes. So should I go to the world description? Will, if that helps you. So this is the world description.
So if we're looking from the top, we can look at which block comes next, and with that next block, we can compare the one after that.
No, basically I'm trying to know. So I'm querying the environment. So it is nothing to do with the robot. I'm just querying the environment. Tell me what are the blocks in this world.
Uh, we have A, B, C, D, and E.
Yes, but we need to write a query or goal to get the answer. So what should be the particular query or goal?
Sir, I'm not sure how we'll write
Oh,
that.
okay. Aryan, would you give it a try?
Yes, sir. So
Yeah.
we can say that X is a block if robot can see X, or on X comma Y, and cx. I mean, y is a block if on x comma y and cx.
Okay, let me rephrase the question. So it is not like whether the robot can see it or not. I'm not asking you whether give me the blocks that robot can see. So I'm asking what are the blocks in this world? So you have to write a query to find that answer. So I'm not looking at the perspective of the robot. So maybe there is another observer who is trying to get the sense of the environment. So is question clear?
I'm not sure, certain.
So anyone will give it a try?
So can we say like if a space is filled, then we call it a box, or like box fills the empty space. Box is an
Okay.
entity which fills the
Yeah,
coordinates.
I'll just request you to look at the world description that is on the screen. So this will give you the sense. It is not that involved. So you just have a look at the statements or facts about the world and you'll get to know readily.
So, so if there's any block in C, suppose C A 1,5, then we'll go on till the position is something comma table.
Okay. So you are talking about a recursive way of doing this. But do we
Yes.
need that really? So you just look at the facts about on. So look at the positional relations. So look at the first argument.
Yeah. So all the elements on the first argument will be
Okay.
the.
Okay. So let us see how we can write that. Okay. So it will be say, so the point is, if something is a block, that will be on something. It might be a table or it might be a different block, right? So basically we'll be writing a query like this. Say this is the block, this is a variable which I want to retrieve. And I really don't care what is there in the second argument. It can be another block, it can be another table, it can be table, right? Now if you run this, so I can see that B has been instantiated with A, then B, then C, then D, then E, right? It's very simple. So does that make sense?
Yes, sir.
Okay.
So can you please show the sorry, sir. Can you please
Yeah,
show
yeah.
the query? Okay, sir.
Okay. Yeah. So let me just explain it a bit. So this is a
Yes, sir.
variable and this is a don't care. I really don't care whether this is a block or this is a table. Only thing I'm caring about is the first argument of the on predicate. Okay.
Okay, sir.
Okay, now how do we go about these pairs of blocks having the same y coordinate? Any idea?
If we can use the on function, like
Right.
previously, whichever we have found out, like from x-axis, if we have found out something, so it will go upwards from that block only. I'm not sure about the query to write. Like if we find like C, if we have found out C, we can go upwards like on B, like whatever is on C. I will
See, you look at the grid. So you have got this line to be the x position, right? So this is the
yes,
x direction and this is the y direction,
right.
right? So I'm trying to find a pair of blocks that have got the same y coordinate, right?
Okay. Yes, oh,
So basically what we know, we just know this on predicate. So Sudeshna, you talked about on is a function or on is not a function, on is a predicate. And you know the difference between predicate and function, right? The predicate. So basically I'll try to find say B1 which has got say y coordinate y, and also on B2 is another block which is having will not be on. Basically, for this we need to look at the C predicate, right? So C B1, I really don't care about the X position. Y position is important for me. Then C B2 Y. So are we done here?
Yes, sir.
So what else we need to do? What else do we need to do?
B comma B1 on B comma B1 and then going on like that.
On B comma B1. Why do you want to do that?
I'm not sure of the question. Like pair of blocks having the same y coordinates, so AD, BD all will be there, na? AB, AD, BC.
Yes. Yeah. So basically, let us refresh this a little bit. So the robot can, this is the robot's perspective. So let me just, this is robot's perspective. So if I add this point.
Then B1, B2 will make a pair.
Yeah, B1, B2 will make a pair, but it might so happen that you may end up with assigning the same value to B1, B2. So in that case, you need to add another predicate saying that B1 is not equal to B2, right? The way to do that is B1 not equal to B2. Otherwise, you can have pairs like A is on A, or A and A having the same Y coordinate, which we don't want to have, right? Okay. So the third question I like to ask is boxes that are not visible. So how do you do that?
Sir, on A comma ground and not C A comma something something.
On A comma ground, there is no ground, so you have table. That's
Sorry.
fine.
On A, yeah, sorry.
Yeah. So on A comma ground or table, then
Okay, it doesn't need to be a table.
yeah, it does not need to be a table. It can be anything, right?
Yeah, A comma something and not C comma A.
Exactly. So let us first write C, A, it can be anything, right? So the way to write not in Prolog is using this operator, not positive, that means negative, right? So if this is satisfied, then not of C will be would not be satisfied, will be false, right? So likewise, we can do the others. So I'm not iterating through all the questions here. So let me first explain maybe this one, or I leave it this and this to you. So here, the question that I'm trying to ask here is to find the Z coordinate of a block, right? So if I say I want to find the Z coordinate of A or B or C, how do you do that? So basically, we know that if a block is on the table, so that means that block has got 0 Z coordinate, right? So this is the base condition. And what is the recursive step? The recursive step is that we say that B is on B0, and we go on computing the Z coordinate for B0, which is Z0, and then we are adding 1 to that to get the Z coordinate of B. I think that makes sense, right? So basically what you have, this, something like this, and you want to know the Z coordinate of this. So basically you first find out the Z coordinate of this block on which this block is placed. So this is your Z0 and Z is equal to Z0 plus 1. Right. So with this, let us move to the different kinds of problems. I'm having Anindita, can you please put off your mic if you're not yeah. So now we'll be analyzing different kinds of problems and we'll try to see how we can model them using Prolog. So we'll be taking examples of three kinds. One is inherently recursive problems, which we have discussed already. Inherently non-recursive problems, and then finally I like to touch upon few problems that involves combinatorial optimization, right? So let us focus on recursive problem. So first problem that I like to highlight is the Fibonacci series, right? So the Fibonacci series can be written in many ways. So let me show you two ways. Yeah, the first way, let me first explain it and then I'll ask you as output what you'll be getting. So we know that the 0th Fibonacci number is 0, right? And first Fibonacci number is 1. And let us assume that the nth Fibonacci number is x. And this is the state that we are concerned about. So first we need to check whether n is greater than 1 because we have already considered 1 earlier, right? First we'll be computing n minus 1, n minus 2 and assign them to n1 and n2 and go on to compute the Fibonacci number for n1 and the Fibonacci number for n2. Then our x will be x1 plus x2. I hope you understand what is a Fibonacci series, right? So can you tell me as output what will you be getting? So as output, what will you be getting? So if I say fib.
Sir, I have a doubt.
Yes, yeah. Tell me.
Sir, do we have to always assign n minus 1 to n1 and then in the bracket write n1, or can we write n minus 1 directly in the brackets?
No, I think you cannot do that because n minus c, what this is doing, I told you this in the last class that here we are evaluating n minus 1 and then assigning to n1, right? Now, if you say n minus 1, if you pass directly n minus 1, I guess that it will take the value of n if n is say 10, it will pass 10 minus 1 without evaluating. So there is a difference. So here I am evaluating 10 minus 1 to be 9 and assigning that to n1. But if you do that directly, you will not be able to find, you are not really calling it for 9, you will be calling it for 10 minus 1. So one difference between procedural language and Prolog language is that Prolog language deals with symbols. So it does symbolic computation. So it matches the head or the goals or matches the predicates, right? So in that case, there will not be any evaluation. So that is the issue.
Okay, sir.
So now, can you tell me what output we'll be getting? You don't need to tell me the exact number, but will we get a single element or list? So that is the question. Any idea?
I think single element because we are doing x is x plus 2. We will be getting the element when we will be the like the total of 10 elements. So like,
Yeah.
I mean, sorry,
So
not total of 10 elements. Like before that 2 elements, the addition of before 2 elements. I think so.
So basically it will not give us a list. It will be giving us a single element, which will be kind of some Fibonacci number in this series, right? Now the question is, if I want to print the entire series, so how do you do that? So of course, for that, we need to store the intermediate values, and list is the best way to store different values. So we'll be talking about a program which will exactly store the intermediate values. So let us try to formulate the strategy, right? So we know that when n equal to 1, so what is our list? Our list is 0, 1, right? So while we are initializing the program, our initialization will be a bit different. I'll explain why I'm doing this. So in the recursive call, I'll not pass this on. Instead, I'll be passing the reverse of this list, right? Now, when we are calling it for n equal to 2, so we'll refresh this list. We will refresh this list to be this. Now, why we are doing this? Or let me do other steps, then you will understand why we are doing this. So for when n equal to 2, what is the number? Addition of these two, sum of these two, we have got 2, right? So we'll be pushing this in the list 2, 1, 0. Then we have this, sorry, 1, 1, 0. It will be 1. One, 1, 0. Now again, we'll be refreshing this list as 1, 1, 0. Then we come at the step n equal to 3. I'll be taking these two, adding this 2 to get 2, and be pushing this in the list 2, 1, 1, 0. And then while we are passing this on the next step, we'll be refreshing this as 2, 1, 1, 0. Now, do you get a sense why we are first place, why we are doing this? I'll be coming to the reversing of the list later. But why we are rephrasing the output to this form? Any idea?
So to get the sum of last 2 elements, after reversing it gets to the first 2 elements.
Exactly. Very good. Thank you. So basically, we want to make sure that in the front of the list, we are having only 2 values, which are basically the last 2 numbers we have computed. And from that, readily we can compute the next Fibonacci number, right? Now, why we are doing this reversing? So the way why we are doing this reversing, that is concerned about the list data structure. So in the list data structure, I can write a list like this, say HTEL. I can write this also as say H1, H2, tail, right? And so on and so forth. So while we are computing the new value, we'll be pushing that in the front of the list. And as we are pushing that in the front of the list, what is happening? Basically, we started with 0, 1, and we are having the first one to be putting this at the front, and we are computing this to putting this at the front. So you see, we are having the list in a reverse order, right? So that's why we have started in a reverse with a reverse list initialization, right? So that means after we have done all the steps, we have to call our reverse function, reverse predicate for this output list, and that will give us the desired list. So that is more or less the plan, right? Now let us look at what we are really doing. So this is the primary function, which is so this is the set or the list where I'll be storing all the Fibonacci number, and this is the number up to which we want to have these Fibonacci numbers. So we just check whether n is greater than 1 because we have already computed this 1 and 0, right? Now we call the main Fibonacci sequence function with this n, and of course as output what we'll be getting a reversed list, reversed Fib series, right? And this is basically the current value, current iteration. So if you have, say, this is I equal to, so let me rename this, should not write n here. So let us have this to be I, and I. So basically I am here storing the count, the step count, right? And finally the reverse list, right? And after we are done, we will call a reverse function. So this is one inbuilt function to reverse the list and store that in the desired variable, right? Now let us have a look at the function that actually does the computation. So basically what we are having, the n, the sequence which will be storing the reverse ordered Fibonacci, and this is the first n value we are starting with, and we are always getting the list in this order B, A, and then the remaining Fibonacci series. So first I'll check whether n is greater than n0. If that is so, we will increment n0 by 1, and then we will be computing the next Fibonacci number by pulling these two values, right? And then we'll be recursively calling this program with n, the sequence, the new value of iteration, which is your I, and we are having a new list here. We are having C, the new Fibonacci number, which we are pushing here, right? And then as we call this again, so these list will be transformed into a form CB, and A will be, sorry, this will be comma here, and A will be added with FS. So A will be added with FS. So this is how we can write a program which will store not only the last number, it will store all the numbers in the Fibonacci series. So let me go to another inherently recursive problem, which is a sorting problem. But you know, you have written bubble sort, selection sort, or insertion sort. They are basically iterative in form. Mostly you have written iterative programs. But when we talk about merge sort or quick sort, something like those can be written in a very nice recursive formulation. So we'll be discussing merge sort here. But before that, let us have a look at how the iterative sorting algorithms, they can be transformed into a recursive sorting algorithm. So let us have a very simple sorting algorithm where we are just selecting the minimum, and then we are putting that in the front of the list, and we are getting the remaining part and sorting the remaining part and appending that with me. So what is the idea that we are trying to explore here? So basically we have got this entire list. So this is our entire list. Now somewhere in this list we have got mean, right? Now all the elements that are appearing before the list, let us call it as before mean. Now these may not be sorted, these may be in any order, right? And whatever elements that are appearing after mean, let us name them to be after mean. And you know, these two are unsorted. Right. So what is the kind of conditions that we need to satisfy? The condition that we need to satisfy that the concatenation of before mean and mean followed by after mean will give us what? Will give us the list, the entire list, right? And of course, we want to store the before mean and after mean to get unsorted list, right? And we will be sorting the unsorted one. So basically, let us store that in a variable like rest sorted, and that will do with the unsorted array. And after we have got this rest sorted, we place this min before rest sorted. So this is the plan. So for this, we need to define the predicates like mean, which is very straightforward. It is computing which one among the two variables are minimum. And using this mean, we can find the smallest element in a list. So this is also very straightforward, right? Now, an empty list is always sorted, right? Now here, the sorting program we have enumerated. Basically, we are implementing what we have just discussed here. So basically, we are placing mean before rest sorted, right? And this together will give us the entire list, right? So the first thing that we are doing, we are extracting the minimum from list, and we are appending before mean with mean after mean to get list. So this we can do with concatenate operation as well, but this append is a built-in function which can be readily used, right? Then what we are doing, we are adding this to or concatenating this to list before mean and after mean to get the rest unsorted, and we are calling this program recursively to get the entire list sorted, right? So with this, let us go to the main program that we were trying to write, is to write the merge sort, right? So let me give you a very brief overview of how merge sort works in a divide and conquer scenario. So how many of you have done divide and conquer programming with merge sort, or any idea about divide and conquer algorithm on merge sort? I hope that you have studied this earlier, isn't it?
Yes, sir.
Okay. So if that is so, let me give a very brief overview of merge sort. Basically, we have a list. We divide the list recursively, approximately in halves, and try to sort the divided lists, and then we try to merge two sorted lists, right? So basically, we have a list which we divide into two. We sort them, and whatever sorted list we get, we do a merge operation, right? And merge operation is implemented in what way? Basically, we'll be taking the first element of both the lists. We'll check whether, so if this is x1 and if this is x2, then we'll check whether x1 is less than x2 or not. If that is less, then we'll be putting that in the merge list, right? And then go on doing the same for the remaining part and the entire part. So this will go on until we have both the lists, at least one of the lists exhausted, right? So for that, first we need to define the merge operation, right? So let us first define the merge operation. So if you have one empty list, you can merge this with one list to get the list itself, right? The other thing also may also be possible. So here you can see I'm writing both the cases, and you know the obvious reason, right? So I'm not sure whether given two lists, which one will be exhausted. It might so happen that this becomes exhausted first, or this becomes exhausted first. So that's why we need to have both these to be here, right? Now let us consider the in-between or intermediate cases. So what we have got two lists. The first element is M1 and the rest of list 1, right? And we have got the other list M2 and the rest list 2, right? So first we'll check if M1 is less than equal to M2 or not, right? So if that is so, I'll separate out M1, and what we are remaining with, rest list 1 and M2 rest list 2. And we call the merge operation for these two lists to get the rest merged. And finally, what we'll be doing, we'll be concatenating these two to get the final sorted list. And if the other way is true, where M1 is greater than M2, you know you'll be doing the reverse thing, right? And I already talked about the how do we divide the list. So basically, this is the merge sort operation. So where you have got the list, and we divide this in halves, and keep on doing this. And finally, we get the sorted list, and we call the merge operation finally, right? So let us have a look at the program to see whether we are implementing the idea that we have mentioned today. So yeah. So we are we are having this base condition of this merge operation. And let us have a look at the case where the minimum 1 is less than equal to minimum 2, right? So we are having two lists. One is starting with mean list 1 and rest merged. And we have, so this is the final merged list, right? And what are the input lists? The input lists are mean 1 rest list 1 and mean 2 rest list 2. So first we check whether mean list 1 is less than equal to mean list 2 or not. Then we call the merge operation or predicate by stating that we have to do the merge of rest list 1 and the other list, which is mean 2 rest list 2. And whatever the result is, we want to store that in rest merged. And we'll be doing the reverse for the other case. So I'm not discussing this. Now for merge sort, we have got two base conditions where the empty, whenever we have an empty list, then that is already sorted. And if we have only one element, that is also sorted, but we are writing that in a different way. Now, so the first thing that we'll be doing in the recursive step, we'll be computing the length of the list because we want to divide that into 2. So we compute the first length to be the half of 2, where we are doing this division operation, and the rest of the length is the second length. So we are having the first unsorted to be a list which has got the length to be first length. So in order to make this predicate to be true, this list will be having a size of first length, and second unsorted will be having a size of second length, right? And if the third condition is that when we append these two, that will give us the entire list, right? And if you do that, you see that this, so in this, for these first two statements, this first unsorted and second unsorted, they will not be instantiated. They will only be instantiated when we call this append predicate, when we achieve this goal. So this will divide the list into two parts. N by 2 from this list will be going to first unsorted and the remaining will go to second unsorted, right? Then we call merge sort on the first unsorted and store the result in first sorted, call merge sort again on the second unsorted to store that in second sorted. And we have got two lists to be sorted, first sorted and second sorted, and we just do the merge operation as we have defined earlier and store the result in sorted, right? So this is the way we can implement again one truly recursive program very easily using Prolog. So let me focus on a particular problem that is a kind of iterative problem to look at, which is basically finding path in a graph. So we have a graph like this, and the idea is that for a source and destination pair, you need to check whether there is a path. If there is a path, you need to list the nodes in the path, right? So let us, I think this code will be a bit straightforward. So let us go directly to the code. So first thing that I'm doing, I am specifying the edges. So this is where I'm defining the network. So this is a directed network that we have defined. So there are two versions of this path. So the first version, what it does, it just tells whether a path exists or not, but it does not provide an output of the list of nodes that are visited in this path, right? So a particular node is having a path to itself. So that is the base condition. And that's why we are saying that there is a path from N to N. Now a path from S to D can be divided from path one edge from S to N. So basically one edge from 1 to 2. And then we need to check whether there is a path from say 1 to 5. Then we can say that there is a path from 1 to 5, right? So we are calling this again with the remaining part to be solved, like N to D. Now, if we want to store the intermediate path in as we explore the graph, so this is what we'll be doing. So we know that from one node we have a path from that node itself. So that node will be having an entry in the list. So this is the place where we are storing the nodes that are visited in this path, right? So we are doing the same thing. Only thing that we are doing, we are adding this S to the list of the nodes that are getting visited. So this T is basically the path that we have computed for reaching to D from N, right? And with that, we are appending S because we have an edge from S to N, and that gives us L. So L is basically the concatenation of S and T. So with this, let me stop here today. So tomorrow I'll be covering two combinatorial optimization problems. And of course, I have there are three tutorial problems that has been formulated. So what you need to do using this ID that I have already shared with you, you need to write solve those problems and upload the PL file. So you can, I have shown you that how to download the PL files from this ID, right? So you need to download the PL file and upload in the assignment place, right? So
will this take place tomorrow only, submission of the three problems?
Yeah, so whatever we do, we can submit. So it is not like that. So I know that you need some time to work on this. So it is a kind of practice that we'll be doing.
Okay, sir.
So don't worry about it. So it's a kind of practice we'll be doing. So whatever you do, you upload.
All right, thank you, sir. So, and I had one more query actually. So we have our second class test coming up next week.
Yeah.
So could you tell us the syllabus for that class test?
Okay, so the syllabus would be the portions that Professor Chakraborty has covered. In that test, the portion that the topics that I have discussed, they will not be there. So it is, I guess it will be only on logic.
All right. Okay, thank you, sir.
So any other questions or doubts?